Hi. So the goal of this video is to further talk about the concepts of Gauss quadrature. And if you haven't seen my first video on this subject, I recommend going back to watch it. But as a quick review, the general idea is that I have some integral that may be somewhat difficult to solve. And I've given this example here where I have a function f of x. I'm integrating from some bound a to some bound b, and I would find the true value of that integral if I was able to do it correctly. But sometimes the integration is very difficult depending on what you're dealing with. So what would be easier is instead of finding the exact integral, we approximate it. And the way that we approximating using this Gauss quadrature technique is to take the integral, and instead of thinking about it as the area underneath one curve, we think about it as the area of n amount of rectangles. So we see on this bottom right picture here that instead of integrating the area exactly, which would be this, I'm instead drawing two rectangles in this case and finding the area of each of those. Now, those two rectangles have some widths that we call C, C1 and C2, and their heights are f of xi, where xi is some point that will determine the height of the rectangle using the function. So we would say that this is, if n is 2, we would say that this is c1, f of x1. That is the same as this area of this rectangle plus c2, f of x2. That is the same as this rectangle's area. And that's an approximation of our original integral. And we discussed how to do that and how to find those coefficients c1 and x1 and all that stuff in my other video. But there are times where we want to have more than two rectangles to improve the accuracy of our integral. However, as I described in the previous video, we would typically use what's known as the method of undetermined coefficients to find what those constants are, c1, x1, c2, x2, etc. But sometimes it becomes too difficult, it becomes nonlinear, it becomes complicated. So instead, what we would like to do is use some sort of reference. And there's a table that exists where, depending on how many rectangles you want, you can easily go look up in the table what your C1 and X1 values are. So you see that if I want one rectangle, C1 is 2 and X1 is 0. If I want four rectangles, I can see here what all of those numbers should be if we have four rectangles or four squares or whatever. I think the rectangles, sorry. Four rectangles for Gauss quadrature. And so on. But we have to learn what the prerequisite is for using this table, because it would be nice to use this table, but if I have the integral from a to b and a is some number and b is some number, and I dramatically change those a and b values, is this table still accurate? And the answer is no. This table is only valid when the bounds of the integral are -1 to 1. So really, we would say that the table would be some integral from -1 to 1. And I'm going to write this as involving a new variable. You'll see why. But we basically have to take our f of x integral and convert it to this other integral that has bounds of -1 and 1. Now let's think about this for a second. If my graph is set up to be between -1 and 1, let's think about our example here with using the table. Let's assume we have one rectangle. It says that the base of that rectangle is 2. Well, that makes sense because that is the width of the whole region. And we find our function value at 0, and that's going to be the height of our rectangle. So if I draw a rectangle, we'll see that this is the area approximation when we include one rectangle. And you'll see that for all these cases, if I look at the 2-point case, we see that each rectangle has a width of 1, which adds again to the span between -1 and 1. It adds to 2. If you go ahead and look at any of these, you'll see that these will always add to 2 because of the fact that we're dividing this bound, this -1 to 1 bound, to separate little widths that will make up our rectangles. So our goal for this video is to understand how do I go from an f of x integral to a g of t integral, which will allow us to use the table. And let's talk about the concepts of this. Essentially, let's say I give you a function that is between, I have some function that I'm integrating, and I'll draw it like this. Let's say I'll draw it pretty low. And let's say it is between 4 and 8. And I'll say that this is f of x. And I want to approximate the integral from 4 to 8 using maybe 3 rectangles, which would require us to use the table, or 6 rectangles, or what have you. So we have to convert this to an integral from -1 to 1 of some new function that will integrate with respect to this variable t. This isn't time. This is just some arbitrary t. So this is my x-axis, and I want to convert this ultimately to an integral that goes from -1 to 1. So what are the differences between these two situations? Well, first off, we can see that the center of our bounds should be at 0. Center of the bound should be at 0. Right? We see that. In between -1 and 1, the center is there. Currently, the center is over here. For this picture, the center happens to be 6. How do I know that? Well, that's going to be the average of the two values. So I'm going to define a variable c, that is the center. That will be the average of my bounds. And in this example, that would be 4 plus 8 over 2, which is 6. So what I would like to do is I would like to take this guy. Maybe I'll try my best to include this here. I want to take this guy and I would like to shift it across so that it is now centered at 0. So how much do I need to move it by? Well, I'm going to take all my x values and I'm going to subtract this center from it. So this shifts it left or right, depending on what c is, but it shifts it to the origin. So what do we have now? Well, let's make some room here. That's our goal. If we shift it towards the origin, we haven't changed the width of this yet. But if I move everything over by 6, for example, if I take the 4, that's x, and I subtract 6, that will ultimately give me -2. If I take the 8 and subtract 6, I will get +2. And we see now that our width is still the same. Our width was 4, it's still 4. But now we are centered at the origin. That is good. We have completed one step of this. The next thing we need to do is note that the width must be 2. Because from -1 to 1, that has to be 2. So I'm going to look at the current width, which will be b minus a. If we come up to here, our width doesn't matter if we shift it or not, but I'll take b minus a. That is the width. And I need to divide that by some number to end up getting me 2. So I'm going to divide this by some letter m. Maybe we can call this like our magnifier or something. That's not the exact name. That's just what I'm calling it to help remember the letters. C is the center and M is the magnifier or the scalar, the thing that is used to take our width and get it to the correct values. If I solve for M, I see that I can just say that this value here will just be the width divided by 2. And this is what we need to divide by. We need to divide by M ultimately. In order to get the width to be 2. So far we have shifted them. Now what I would like to do is divide that by M. And this will ultimately give me my correct t-axis, which is going to be between -1 and 1. And let's do this for this example. Our original bounds, A was 4, B was 8. Again, these are x. We need these to change ultimately to -1 and +1. So let's confirm that this is true. I told you that C is the center, which is the average of those two values. That was 12 over 2 was 6. I said that this magnifier, this M, is going to be the width divided by 2. That's what we learned from doing this math here. We're trying to get a width of 2. We divide by some arbitrary number. And if I solve for that arbitrary number, we have an equation for it. B in this example was 8 minus A was 4 divided by 2. We have to divide all of our numbers by 2 to get the correct value. So basically, I have x minus 6 over 2 is equal to t. So let's plug in A. Let's just see what happens. We'll just check to make sure we're correct. If I do A, which was 4, minus 6 over 2, we get -1. That's what we want. We took this 4, we shifted it, and then once we divide this number, we end up getting -1. If I do the upper bound, which was 8, we get 1, which means that we are correct. Good. So this is how we find our M and our C, simply using the bounds that we were given at the beginning of the problem. But I still haven't converted this integral yet. So as I have this, and I am now able to use -1 to 1, but I have to replace my function with this new variable t. And I just learned that x minus c over m is equal to t. So let's try to do some substitutions. I have this function of x here. Let's solve for x so we can substitute in what our t value or what our function of t is ultimately going to be. If I multiply both sides by m and add c, I get that x is equal to mt plus c. So that means that my integral from a to b of f of x will become f of mt plus c. And we want to find dx now, a differential of x. So I'm going to take the derivative of both sides, where m is a constant. And then we take the differential with respect to t. So that means that dx is going to be m dt. This whole thing here, with the extra factor of m, that is my g of t, which is now valid for really what this should be. This should be -1 to 1 here, because I'm making these substitutions. This is going to be the same as g of t dt. And now I'm able to do the problem with my g of t with this extra factor of m. What is this factor of m? Why do I need this extra factor? Well, let's go back to our original problem. I'm going to try my best to focus on this blue curve. This blue curve we have shifted. Let's try to line them up. And then I'm going to take it and I'm going to go ahead and squeeze it together to fit within my bounds of -1 to 1. This f of x here, I need to squish. That's what I have right now. If I'm going to take this volume, or sorry, this area, and combine it and make the bound smaller, in order to maintain the same area, the f of x has to be increased in height. So now f of x is not this thing. Oops. Perhaps it looks more like, and I'll go ahead and erase these old lines. Perhaps it looks more like this. Because of the fact that we are squishing this area, we have to make sure that we do not lose any area. So when we squish it in x, we will elongate it in y. If you've taken mechanics of materials or mechanics of solids before, this is very similar to the idea of Poisson's ratio. If I take an object and I go ahead and compress it, due to Poisson's ratio, we expect it to be stretched or compressed in the other direction, depending on what we're doing in our main direction. So if I pull in x, I expect the values in y to decrease. If I compress in x, I expect the values of y to increase. Same thing here. I'm taking this area, I am squishing it, and because I'm squishing it, it has to go up or elongate in the y-axis. That is what this m is doing. This m is ensuring that we multiply by some factor in order to ensure we're accounting for any missing area. And that's a general theory. I'll do one example. Let me just pull up an example from my notes for completeness. But the general thing we're going to do is we'll be given some function f of x, and we need to figure out how to change the bounds and then do it for our new function. So the example that I give in my notes is, let's use a 3-point quadrature. So three rectangles. And I say approximate this integral, x to the 0.2 x dx. Now, if I want to use 3 points, it would be difficult to come up with the relationships for those. What I would rather do is write this from -1 to 1 with this new function g of t dt. So let's figure out our shifts, because ultimately what I'm going to do is take my f of x dx. This is going to be written as -1 to 1 f of mt plus c times m dt. That's what we just showed here. So let's find our m and our c. Well, our c is our center point, which is the average of the two bounds. So that would be 1 plus 5 over 2 in this case, which is 3. And our m is the width halved. So it's going to be 5 minus 1 over 2, which is going to be 2. So that means now that I'm going to have an integral from -1 to 1. That is f of 2t plus 3 m dt. This notation here says to plug 2t plus 3 into our original function. So original function was this x to the 0.2 times x. This is going to be -1 to 1. Instead of x, we're going to do 2t plus 3. That is our x. And now we have 0.2 times x in the exponent. 0.2 times x times 2 dt. And now this whole thing here is my g of t that we will use in our table. I'm going to approximate that g of t using 3 rectangles. And you see I'm doing x1, x2, and x3. That just matches the table notation, which has it in terms of x. If we come up to the table, we can see that these are all x values. Let's see if I got lucky with the paste. Nope, oh, I did a little bit of it. So what we're going to do is we're going to look at the 3-point case. I'll try to just copy this down. Where we can see, what our widths and our x values are for the 3-point case. So this is going to be approximated as C1, which is 0.556. I'll just round it for simplicity, times the function evaluated at negative 0.775, plus the width of the second rectangle times g, plugging in that x2 value, which is 0, plus 0.556 g of 0.775. Again, that is just coming from these values here for 3-point quadrature. Just to show an example, I'm going to calculate one of these. It's going to be 0.556 times g of negative 0.775. Well, here's our g up here. This is going to be 2 times, let's be careful here, 2 times that negative 0.775 plus 3 raised to the 0.2, 2 times negative 0.775 plus 3. And we can't forget this other 2 on the outside. That is from our m, our scaling factor, that will go ahead and make sure that we account for any area we lost when squishing. Now we have increased the height. If you go through this math, you end up getting 2.228. And you would have to do that type of thing for each term, each rectangle. We just found the area of the first one. The area of the others, if you want to go ahead and do this on your own, so this is A of the first one. A of the second one is 3.866, and the area of the third one is 7.9386. And ultimately, if you add those together, we would say that our integral from A to B of x, I'll do it exactly, from 1 to 5 of x to the 0.2x, we say that that's equal to the integral from negative 1 to 1 of this 2t plus 3. I'm just rewriting exactly what we wrote before. That ends up being approximately equal to 9.08. And if you did find the true integral of this, you would see that your relative true error is around 0.01%. It's a pretty good method. Understanding how to convert any integral to one that we can use the table is very useful to us. I'm hoping that this was helpful. If you have any concerns or doubts, please let me know. Okay, thank you. Bye.